Hi guys, in this short video we're going to look at how to calculate the number of atomic particles, protons, neutrons and electrons in isotopes. So I've drawn this table with a few examples. Here we have normal hydrogen, the most common form of hydrogen, and two of its isotopes. So the small number from the periodic table, that gives us the atomic number, which is the number of protons, which is equal to the number of electrons. This is why atoms don't have a charge, they're neutral. Then the mass number, this is the bigger number on the periodic table. That is the number of protons and neutrons. So to get the number of neutrons in these isotopes, what we do is mass number minus atomic number. So for this one, 2 minus 1 gives 1, and for this one, 3 minus 1 gives 2 neutrons. Then I've got another example. So we've got the common form of carbon here and two of its isotopes. So the atomic number is 6, which gives us the number of protons and electrons, which stay constant for the isotopes. If the number of protons were to change, then it would be a different element altogether. If the electrons were to change, it would be an ion. So only the neutrons change. So to get the number of neutrons, we do mass number minus atomic number. So 13 minus 16 gives 7 for this isotope. 14 minus 6 gives 8 for this one. Now one more example calculation I'd like to look at for isotopes. How to calculate relative atomic mass. So this is the relative atomic mass. It's the big number from the periodic table. Now confusingly, that's also called atomic number, but it is atomic mass. Everything has lots of different names, it's very confusing. So calculating relative atomic mass, the big number from the periodic table, from something called relative isotopic mass. So I've got two example questions here, and I'm going to explain how to work them out. Calculate the relative atomic mass for a sample of potassium containing 92.10% potassium 39, 0.08% potassium 40 and 7.82% potassium 41, and it's just 1 mark. So I've abbreviated here relative atomic mass. What we do is times the percentages by the mass number of the isotope, and we add these together. Now don't forget your brackets, otherwise you might end up with a funny answer. And then we divide by 100 because we're dealing with percentages. And usually we're expected to give our answer to 1 decimal place. So you could pause the video here, pop that in your calculator and make sure you can get the right answer. For the second example, it's very similar. The relative isotopic mass for chlorine 35 is this. So it's given us really accurate values here. So because it's given us these values, this is what we're expected to use. And for chlorine 37 is this number. Calculate the relative atomic mass of chlorine. And you need to know the percentage abundance. So percentage abundance, it's just these values. It means how common, how much of that isotope you have. Now sometimes it might be given to you in graphical form, so in a graph. I forgot to show you. So for that potassium example, they might have given it to you like this. So these kinds of graphs, we get them from a machine called a mass spectrometer. The y-axis is percentage abundance, so how much we've got in a percentage. The x-axis is something called mass to charge ratio. Z is charge. And this is just basically the mass number of the isotope. Okay, so back to this example. So what we do is very similar. We times the percentage abundances by the isotopic masses that we're given, and we use all the numbers in this value that we're given, and the same thing here for this one. Okay, so since we're given really accurate values, let's give our answer to 2 decimal places. Now normally the question will specify how many decimal places it wants. So 35.45. Now Notice that even though we've used these really accurate isotopic masses, if we round this to 1 decimal place, it still comes out as the same value for chlorine on the periodic table, which is 35.5 for the mass number. So really, if we're using mass numbers to 1 decimal place, it makes no difference whether we use 4 decimal place, really accurate ones, or 1 decimal place values. So I hope that was helpful. Just a quick video on isotopes and the calculations. If it was, please like and subscribe. Any suggestions or comments, please comment below. Thank you.